Welcome to the Explainer, everyone. Today we're diving into a truly fascinating intersection of agriculture and renewable energy. We are looking at this incredibly innovative system that takes something we usually just consider an annoying nuisance, the waste heat generated by solar panels, and literally transforms it into a superpowered tool for sustainable farming. It's just a brilliant example of taking a massive inefficiency in one system and using it to totally solve a bottleneck in another.
Think about this for a second. We all know solar panels soak up the sun's rays to make electricity, right? But they also absorb a massive amount of raw heat, and that heat actually degrades their electrical performance. Well, what if, instead of just letting all that thermal energy dissipate into the air, we could basically act like a giant vacuum, harvest it, and then use it to supercharge the microbial life in our soil? That is the exact waste-to-wealth hack we're unpacking today.
Okay, let's dive into this. Here is our roadmap for today. We're going to start with the composting bottleneck, move on to the agrivoltaic solution, break down the PV thermal behavior, see how we can actually harvest that dissipated heat, and finally, look at the real-world impact on composting.
Part 1. The composting bottleneck. So, turning organic waste, things like sheep manure and straw, into nutrient-rich fertilizer requires heat. And historically, farmers have had two main choices for this kind of aerobic composting. You can go with passive aeration, which sure is cheap and low energy, but it's incredibly slow. Plus, it often suffers from these dreaded cold spots where pathogens can just comfortably survive. Or you can use active forced aeration. This is fast, it's effective, but to reach the goal of a 65°C compost pile, farmers often have to literally pump in 80° air using these massive external electric heaters. I mean, that is a huge energy-intensive drain on the power grid.
And the thing is, you can't just skip the heating process. To properly humidify manure and straw, the tiny microbes doing all the actual hard work in there require highly specific conditions. They are picky. They need a carbon-to-nitrogen ratio of 25:1 up to 40:1, an ideal pH range of 6.5 to 8.5, and absolutely most importantly, they need a thermophilic environment of greater than 55°C for fast, effective sterilization. Maintaining that heat is absolutely crucial. But like we said, electrically, it's incredibly expensive.
Moving to part 2, the agrivoltaic solution.
This brings us to a seriously ingenious workaround. So the crucial point here is that solar photovoltaic modules, PV modules, basically act as giant unintentional space heaters. Depending on the tech, a solar panel only converts about 15 to 22% of incident sunlight into actual electricity. The vast majority of the sun's energy is just absorbed directly as heat right into the module itself. Rather than paying a fortune to run an electric heater, we can essentially just vacuum up this wasted thermal energy right off the back of the panel. The mechanics of the system are surprisingly elegant too. Step 1 involves just installing a thin aluminum sheet behind the solar panel, leaving a 2-inch rear air gap. This creates a plenum, basically an enclosed airspace for PV waste heat collection. Step 2 uses a super simple, low-power 12-volt DC vacuum to pull a continuous flow of air through that gap, collecting all that trapped heat. And then, Step 3 takes that freshly warmed air and shoots it directly into the bottom of the compost pile through perforated aeration tubes.
And this brilliantly illustrates the whole physical setup. You have these polystyrene composting boxes situated directly beneath the PV panels. By placing them right in the footprint of the solar array, the system completely minimizes the distance that hot air has to travel, which means less heat loss. Meanwhile, the panels above provide nice protective shade for the bins below. It takes all this complex thermodynamic theory and grounds it into a very practical, farm-ready reality.
Part 3. PV thermal behavior.
Now, getting into the core data from the testing, the sheer amount of thermal accumulation here is massive. Look at this. While ambient air temperature averaged around 34.1°C, the PV surface temperature averaged a scorching 49.6 degrees, and it peaked all the way up to 58 degrees. When they measured the air at the outlet pipe, meaning the air that was actually pulled through that back gap, it averaged 38.3°C. We are looking at a huge measurable transfer of heat that would normally just blow away in the wind.
These numbers completely validate the whole system. The PV surface delta shows it sits at a staggering 15.5 degrees higher than the surrounding ambient temperature. And by pulling air behind that surface, we achieve an outlet air delta of a 4.2°C heat gain. That specific harvested heat proves this fluid heat transfer model is working perfectly. Even more impressively, the outlet temperature remains highly stable right at that 38.3 degree mark, giving us this steady, reliable stream of warmth.
Now that stability,
That's no accident. The aluminum plenum doesn't just collect the heat, it acts as a really critical thermal buffer. When you get what they call transient solar spikes, like say a heavy cloud passes over and the sun vanishes for a minute, then comes back, the aluminum actually smooths out those temperature fluctuations. This is so vital because you really don't want to shock those delicate microbial ecosystems in the compost pile with a sudden blast of cold air.
What's really fascinating here is a sort of paradox in the statistical correlation. When researchers looked at the relationship between ambient temperature and the PV surface temperature, there was a moderate positive correlation, which, makes sense. Hotter days mean hotter panels. But the correlation between ambient temperature and recovered thermal power was a moderate negative, meaning lower ambient temperatures actually lead to a higher calculated heat difference at the inlet tube. So essentially, it proves that this system remains incredibly reliable and effective even when the weather starts cooling down.
Let's move to part 4 and see how this builds. Harvesting dissipated heat.
To translate all this thermodynamic theory into tangible energy savings, researchers used a standard fluid heat transfer model to calculate the continuous heat recovered. It comes out to a steady trickle of 1.27 watts of recovered thermal power. Now, sure, that might sound a little small on a per-second basis, but remember, this is continuous, totally free energy being pulled the entire time the sun is up.
When you extrapolate that constant 1.27 watt trickle over the course of a year, basing it on a standard 12-hour daytime window, it adds up to an annual thermal harvest of 5.548 theta kilowatt hours. That is over 5.5 kilowatt hours of pure thermal energy generated with absolutely zero additional carbon emissions and zero strain on the electrical grid.
Which brings us to part 5, impact on composting. So armed with all this free, zero-emission heat, let's bring the narrative full circle, right back to the biology of the farm. By pumping in that 38-degree preheated air instead of cooler ambient air, the system completely protects the microbial ecosystem. First, it ensures thermophilic stability, minimizing those convective heat losses associated with cold aeration, which massively accelerates decomposition. Second, it really aids in moisture preservation, keeping the pile right in that sweet spot of 45 to 60% humidity by eliminating cold spot drop-offs and condensation issues. And it does all of this running purely on a simple, low-power DC vacuum.
Oh, and beyond just the heat transfer, this vacuum aeration method solves another age-old farming complaint: the smell. Because the system is pulling air through the pile via vacuum, rather than just letting it sit there or mechanically turning it open to the wind, it effectively traps and manages the odorous gases common in agricultural waste, which goes a long way in avoiding local environmental and community issues. Your neighbors will definitely thank you. And honestly, this technology is just getting started. Engineers are already looking into future optimizations, like integrating variable speed vacuums that can automatically adjust themselves based on solar intensity. They're also exploring the use of pebble beds or phase-change materials to actually store that daytime heat so it can be slowly released overnight, ensuring true round-the-clock efficiency. Even just simple tweaks like alternative duct configurations or changing pipe diameters could maximize the convective heat transfer even further.
Which leaves us with a truly exciting prospect. This system proves that what we currently call waste is often just a resource we haven't quite figured out how to plug in yet. I mean, if we can capture the sun's wasted heat right off a solar panel to literally breathe life into our soil and accelerate composting, what other hidden energy is just waiting to be harvested on the modern farm? Thanks so much for joining me for this explainer, and I hope it sparks some brand new ideas about how we view energy inefficiencies.